Okay, so today we are going to be learning the first lesson of Chapter 3. If you want to write the title of Chapter 3, it is Quadratic Equations and Complex Numbers. It's the title of the chapter. Okay, this particular lesson, 3.1, is called Solving Quadratic Equations. Okay, so in this lesson, we are going to learn 3 of the 4 methods to solving quadratic equations, okay? Solving quadratic equations is the same as solving any equation. Basically, it's finding the value of x that's going to make the equation true, okay? So if you're going to look at this particular example, you should notice that instead of y, we have 0, okay? Because if it was x and y, that would have infinitely many solutions. Since we remove or replace y with 0, now I can solve for just x, okay? When we're solving quadratic equations, we have different names that we give for that solution, that we give to that solution, okay? We could call it a solution. We could call it a root. Later on in the lesson, we're going to see that we could call it the zeros of the function, and they're also referred to as the x-intercepts of the equation, okay? So, some of the methods that we're going to learn today. First is graphing. Okay, if you want to find the solutions to an equation, you could graph the function and find or identify the x-intercepts. Those are going to be the solutions. And if you think about it, we're replacing y with 0, replacing this y with 0, which means we're not going up or down, which means we have to be somewhere on the x-axis, okay? So graphing, you just graph the function as you normally would, using the axis of symmetry, the vertex, the a value to stretch, shrink, or reflect the function, and then whatever the x-intercepts are, that would be your solution, okay? The other method is using square roots, okay? In this method, I like to think of it as just isolating the variable, okay? Using inverse operations. So you can't always use this method. You can only use it when there's just one visible x value that you're isolating or trying to isolate. Okay, so what does that look like? If, for example, you have 4x squared minus 30 plus, or not plus, equals 16, okay? I can only visibly see one x value there. I know that there's technically 2 because it's x squared, but I can only see 1. So in this case, I could solve by adding 30 to both sides, dividing by 4 on both sides, right? And then isolating then taking the square root of that, okay? And remembering that when I do that, I have to include the plus or minus on both sides. That could be simplified further, but I'm going to just leave it there for now as an example. Okay, so that's an example of isolating the variable or using square roots. We can use that method here. In an example where we can't isolate the variable would be something like 4x squared plus 16x minus 30 equals 12. Okay, here I have 2 x variables that I can visibly see. I can't combine like terms. I can't isolate the variable, so I would be forced to use a different method, okay? So isolating the variable or using square roots does not work there, okay? The last example is, or the last method, sorry, is factoring. So in this case, you make sure that the equation is set equal to 0, you factor, and then you solve using the zero product property, which we will look at later, okay? So let's just begin with the first example, okay? Let's do 1b first, okay? So if I want to solve this equation using graphing, I have to start by moving everything to one side, okay? So I'm going to take this negative 4x, I'm going to move it to the left side. So this is going to become negative 2x squared minus 4x minus 2 equals 0. okay? Now, because it's an equation, if I look at this and I don't like the fact that there's a negative, or I don't like the fact that there's a negative 2 as the coefficient of x squared, I could divide everything by negative 2, okay? That is fine. You're allowed to do that since this is an equation, okay? And what that gives us now is x squared plus 2x plus 1 equals 0, okay? And because that's an equation in standard form, I'm going to use the steps of graphing a standard form equation to graph this function. So axis of symmetry, we do x equals negative b over 2a. So you would have negative 2 over 2 times 1. So this is just going to be negative 1. Now that I have that, I have to plug it back into the equation. You could plug it in here. You could plug it in here. Doesn't really matter, okay? So negative 1 squared plus 2 times negative 1 plus 1 is going to give us 1 minus 2 plus 1, which is just going to give us 0, okay? So that means that the vertex for this function is negative 1, comma, 0. Okay, I'm going to graph all of this on my axis, on my xy plane, so that I can then continue graphing and find the x-intercepts. Okay, so that is the axis of symmetry. The vertex is negative 1, comma 0, so it's actually the vertex and the x-intercept, okay? And then I have a y-intercept of 0, comma 1. I have the point that mirrors it. Now, because this has no vertical stretch or shrink, this function, or this equation, has no vertical stretch or shrink, I'm going to follow the parent function, which goes over 1, up 1. So that's those points. And then over 1, up 3, which are these points. And then over 1, up 5, which are these points. So that is the graph of my function. And again, now that I have it graphed, I can identify what the x-intercept is, which is also going to represent the solution. So in this case, the solution to the equation is negative 1, okay? If you wanted to check your answer, you could plug it into the original equation here, or you could plug it into any of the transformed equations. As long as you get a true statement, you know you did it correctly, okay? I do want to point out that we solved this equation graphically, but we could have also solved it by factoring, okay? If you notice, this equation in factored form is x plus 1 times x plus 1, because 1 plus 1 gives us 2, 1 times 1 gives us 1, okay? So remember the factoring methods. So you could have also solved it like this, which I think is much easier. I think a lot of times graphing tends to be more time-consuming and less efficient, but it's still an effective method of graphing, okay? All right, let's do example 1a. Here, again, it's in standard form. I don't have to move everything to one side, so I can go straight to axis of symmetry and vertex. So axis of symmetry formula, x equals negative b over 2a. Your b value is negative 1, so that's negative 1, 2 times 1, which gives us 1/2. Don't love that number, but fractions don't scare us, so we're going to continue. Okay, now that I have the axis of symmetry, I can find the vertex by plugging that value into the equation. So that means I'm doing 1/2 squared minus 1/2 minus 6. That's a 2 there. Okay. 1/2 squared is 1/4. I want to get common denominators, so I'm going to just immediately change this to 2/4. Same with this. I want it to have a denominator of 4, so I'm going to convert that to 24/4. Okay? So when I add all this together, I'm going to get negative 26 plus 1, negative 25/4. So that means that the vertex for this function is located at 1/2, comma, negative 6 and 1/4. So it just keeps getting worse. All right, so that's the vertex. Not nice, not enjoyable. To be honest, at this point, if I was solving this equation by graphing, I would probably stop and use a different method because it just seems like it's too complicated. And to be honest, I gave you this specific equation for a reason to kind of show that, the fact that graphing this one is way more complicated than and any other method that we could use. So that's the vertex. I'm going to graph the y-intercept, which is -6, the point that mirrors it. And then I'm going to use the a value to keep graphing. And since the a value is 1, I know it's just like the parent function. So I'm going to go over 1, up, I'm going to go over 1 and up 1. So that means I am at 1.5, comma, -5 1/4. This is really just horrible. And going to keep doing the parent function. So now I'm going over 1, up 3. Over 1, up 1, 2, 3. Sorry, that was 1, 2. This is 3. Okay, and the point that mirrors it on the other side, so over 1, up 1, 2, 3. The parent function then goes over 1, up 5. So over 1, up 1, 2, 3, 4, 5. So about here. And the point that mirrors it on the other side. Okay? So this is more or less the function. Okay. Now, when it comes to graphing too, you never know for sure, unless you're graphing in intercept form, whether or not you actually cross the x-axis at those points, or if you just graphed it a little bit off and you really cross the x-axis at like, I don't know, 3.1 or something like that. So again, this is kind of just to show that graphing is not really the best method to use. When it is useful to use graphing if you have a graphing calculator, because you could just plug that equation into the calculator and get the answer, okay? But so it looks like the x-intercepts are -2 and 3. The only way to really confirm it is to convert this to intercept form, okay? So again, that means I have to factor it. Two numbers that multiply to -6 but add to -1 are going to be -3 and +2, okay? So since I now have it in factor form, I can confirm that the solutions are -2 and 3, because remember, we take the opposite of whatever that value is, okay? So to conclude, graphing is usually not the best method, but it's still one that you should know, and it is useful if you have a calculator accessible. Okay? All right, let's continue. When solving quadratic equations using square roots, you can use properties of square roots to write your solutions in different forms. When a radicand is in the denominator of a fraction, that sentence makes no sense. I apologize. So when you have a radical in the denominator of a fraction that's not a perfect square, you can multiply the fraction by an appropriate form of 1 to eliminate the radical from the denominator. This process is called rationalizing the denominator. So rationalizing the denominator is when we get rid of the radical from the denominator, okay? You don't want radicals in the denominator because it just makes things way too complicated. So, for example, if I have the square root of 2 over the square root of 16, this is fine because I can just simplify that to the square root of 2 over 4. Why? Because 16 is a perfect square, okay? However, we could say this is example 1. However, if you had a problem where the denominator is a radical and it's not a perfect square, this is where you have to rationalize the denominator. So, for example, if I have the square root of 2 over the square root of 3, I can't leave that radical 3 in the denominator. I have to get rid of it. So I can do that not by getting a completely different fraction, but just by rewriting it in an equivalent form. Just like in the same way that 1/2 equals 2/4, I can rewrite this by multiplying the top and bottom of the fraction by some number, okay? Now, if I want to get rid of the radical in the denominator, I need to make it a perfect square, so a number squared. The easiest, most straightforward way to do that is to just multiply the fraction by whatever the denominator is, okay? Because then this becomes root 9, or you could think of it as being 3 squared, but no matter how you think about it, 3 squared, the square root of that, or the square root of 9, is still just going to be 3. Okay? And then in the numerator, those are both not perfect squares, so I would just write them as the square root of 6. Okay? And again, this fraction is the same as this fraction. It's just written in an equivalent form. Okay? So let me just give you one more example to make sure we're understanding this. If you had the square root of 11 over the square root of 6, what would you do? You would multiply the top and the bottom by the square root of 6, because this would give you the square root of 36, which is just 6. And then in the numerator, we would have the square root of 66. Okay, now I know what some of you might be thinking. You might be wondering, can we simplify this? The answer is no, okay, because 66 is under the radical, 6 is not, and the square root of 66 is really some decimal. It's 8.1246. So 66 divided by 6 is very different than the square root of 66 divided by 6. Two very different things, okay? And you can see it just by looking at what the calculator outputs for both those, okay? So it's not the same thing. We cannot simplify further. That would be our final answer, okay? All right, moving on. So example 2, we want to solve each equation using square roots, which essentially means we want to isolate the variable, okay? All you're going to do is use inverse operations to do that. So get x by itself. How do I do that? I begin by adding 31 to both sides, dividing by 4 on both sides, and then lastly, square rooting both sides, which anytime you square root both sides of the equation, you have to remember to add, very, very important, the plus or minus, okay? So this is going to equal plus or minus root 20. Now, you can't leave your answer like that. You have to simplify it further if you can. The way in which you do that is you look at this number under the radical and you ask yourself, does 20 contain any factors that are perfect squares? And if you don't know what a perfect square is, just remember it's a number squared. So some of the perfect squares, if you wanted to make a list, some of the perfect squares are 4, because 2 squared gives you 4, 9, because 3 squared gives you 9, 16 from 4 squared, 25 from 5 squared, it was about a skip, 36 from 6 squared, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is 169, I think. Clear. Yep. And so on. Okay, so is there a perfect square that goes into 20 evenly? The answer is yes, right? 4. So I can rewrite this as 4 times 5. What's the square root of 4? 2. So I take it out of the radical. 5 is not a perfect square, nor does it have a factor that is a perfect square. So I would leave my answer like that. Okay, let's do the next one. Again, we're just isolating the radical. So the radical. We're isolating the variable. So we're going to subtract by 9 on both sides. Divide by 3 on both sides. Square root both sides. Remember to add the plus or minus. And you get x equals plus or minus root -3. Now, you cannot have a negative under the radical, so at the moment, all we're going to say is that there is no, and this is important, no real solution. Okay, there is a solution, it's just not a real one. Okay, we will learn about that in a later lesson. Okay, so that would be your final answer for B. For C, this one looks a little bit weird. Same idea though. I want to isolate the variable. So how do I do that? I need to get rid of everything else. The difference in this problem is just we're going to do multiplication first instead of subtraction or addition. Okay, so I need to get rid of what's on the outside of the parentheses first. So I'm going to multiply both sides by 5/2. Okay, 5/2 times 2/5 cancels, so I'm left with x plus 3 squared. And then 5 times 5/2 is 25/2. Now I need to get rid of this power of 2, so I'm going to square root both sides. Anytime we do that, we add the plus or minus. So we now have x plus 3 equals plus or minus the square root of 25/2. Now, I know what the square root of 25 is. It's 5. So I'm going to rewrite this as 5. And then I don't know what the square root of 2 is. I mean, it's some decimal, right? So I'm just going to leave it like that for now. And then subtract by 3 on both sides. You get -3 plus or minus. Okay, now let's address this. I could leave it like that, but we just talked about how that's a big no-no. So how do I get rid of the radical in the denominator? I have to multiply the top and bottom by whatever the denominator is. Now keep in mind, this is really just 1. Root 2 over root 2 is just 1. So I'm not changing anything. I'm rewriting it in an equivalent form, okay? So what is this going to be? 5 root 2 over the square root of 4, which is just 2. And that is your answer. Okay. So far we have covered 2 of the methods. So now let's go to the last method, okay? If we want to solve by factoring, we have to move everything to one side. It doesn't really matter if it's the left or the right side, completely up to you. What does matter is that everything is moved to one side and that the other side of the equation is set equal to 0, okay? This is very important. Once you have it set up like this, then you can factor the equation and use the zero product property to solve. Okay, what does this mean? What is the zero product property? Basically what it says is that if I have 2 quantities that multiplied together give me 0, what are possible values that x and y could be? Well, I could have 2 and 0 because that equals 0. I could have 4 and 0 because that equals 0. I could do -3 and 0 because that equals 0. I could switch it up and do 0 and 10 because that equals 0, or 0 and 15 because that equals 0. I could even have 0 times 0. What is it that every single one of these have in common? It's the fact that at least one or both have to be 0 in order for the product to be 0. So this is the idea. If I give you a polynomial in factored form, x minus 4 times x plus 6, okay? If I have 2 quantities that multiplied together give me 0, then what that means is either the first one has to equal 0 or the second has to equal 0. Or they could both equal 0, okay? But this is the idea. So in order to use the zero product property, you need 0, and you need there to be a product, a multiplication of 2 things, okay? Which is why you have to factor, because by factoring, you create this multiplication, okay? Now, it has to also equal 0 because, let's say I had x minus 4 times x plus 6 equals, I don't know, 20. Well, there's so many different pairs of numbers. Well, not so many, but there's definitely more than just one possibility that multiply to 20, okay? And because of that, it's like I don't know what to set x minus 4 equal to. I don't know what to set x plus 6 equal to. Should I set them equal to 2, to 10, to 5, to 4? You know, it's just too many possibilities, too complicated, so we don't do it. Okay, it has to equal 0. All right, let's look at the first one. So here we want to solve by factoring. Again, we need 0 and we need a product. So I'm going to move the 45 to the other side of the equation so that I have 0 on the right side. And now I'm going to factor so that I have a product. What are two numbers that multiply to negative 45, but at the same time add to negative 4? Let's see. 9 and 5, perhaps, with the 9 being negative. That does multiply to negative 4, and it does add to, it does multiply to negative 45 and add to negative 4. So, in factor form, this is x minus 9 times x plus 5, which means that either x minus 9 equals 0 or x plus 5 equals 0. And this is why, whenever we had the numbers in the parentheses, we would always just make it the opposite sign. So your two solutions are negative 5 and 9. Now, if we were to graph this equation, what would the x-intercepts be? The x-intercepts would be 9, 0 and negative 5, 0. Okay, just to connect it to what we did earlier. Very good. Moving on. We know that the x-intercepts of the graph of f of x equals a times x minus p times x minus q are p and q. What form is this? This is intercept form. Don't forget that, okay? We know that p and q represent the x-intercepts, which also are the solutions to the equation. Because the value of the function is 0 when x equals p and x equals q, right? The function, meaning the y value, is 0 at the x-intercepts. This is why the numbers p and q are also referred to as the zeros of the function, okay? So a 0 of a function is an x value for which f of x or y equals 0. So if we want to find the zeros of this function, we have to begin by replacing y, or f of x, with 0. Okay. Now, we've learned 3 different methods at this point, so could we graph this? Yes. If you had a calculator, I would say that's probably an easy way to find the solutions. Let's pretend like we don't, okay? I don't want to graph it because graphing is too complicated. I can't isolate the variable because I have 2 visible x values, 2 x variables, so that makes it impossible to isolate, which means I have to factor this. Now, it's not as simple in this particular case as what two numbers multiply to negative 11, not multiply to negative 11, multiply to 12 and add to negative 11, because this particular problem has a coefficient for x squared of 2. So if I tried to think of numbers that multiply to 12 and add to negative 11, there are none. 6 and 2, 4 and 3, 12 and 1, nope. Nothing works, even if I make them all negative, okay? So here, I have to use a method which is referred to as splitting the middle, or the AC method, okay? This has a lot of steps, so I'm going to write them. The first step is multiply A and C, okay? So in our specific problem, we're going to multiply 2 and 12, which gives us 24. Okay, so now I'm thinking of two numbers that multiply to 24 but add to negative 11. So I need numbers that multiply to whatever AC is and at the same time add to B, whatever our B value is, okay? So what two numbers multiply to 24 but add to negative 11? Let's see. We got 8 and 3. If we make that negative, that does add to negative 11. Perfect. So now what I'm going to do is I'm literally going to split the middle. I'm going to take that middle term and I'm going to split it into these two values. Okay, now notice negative 11 has an x associated with it. So negative 8 and negative 3 need to have x's associated with it. Okay, and then everything else stays the same. I still have 0, still have the equal sign, still have 2x squared, and still have 12. Okay, so that would be our third step. Split the middle term using, that's a G, the two numbers from step 2. Okay. Then step 4 is going to be factor by grouping. See how important factoring is? I hope you guys remember this and that I'm not speaking Chinese. Okay, what is factor by grouping? It says if I have 4 terms, I'm going to group the first 2 terms together and take out whatever they have in common or whatever the GCF is. And I'm going to do the same for the last 2 terms. So what is it that 2x squared and 8x have in common? They have a common factor of 2x. What's left over is x minus 4. Because what is 2x times x? It's x squared. What is 2x times negative 4? It's negative 8x. So I'm not changing anything. I'm just writing it in a different form. In the last 2 terms, what do they have in common? Well, they have a 3 in common. So this would be negative x plus 4. But the goal is I want this and this to be the same. So while I could take out a positive 3, I'm going to take out a negative 3 so that I get the same 2 terms in the parentheses. So this would be now x minus 4. Again, we can check our work. Negative 3 times x, negative 3x. Negative 3 times negative 4, positive 12. I am not changing anything. Then the last step is to put it in fully factored form. The parts they have outside the parentheses times the part inside the parentheses. Okay? Now, again, if you wanted to double check this to make sure this is correct, just FOIL it. Okay, if we do first, we get 2x squared. If we do outer, we get 8x. If we do inner, we get negative 3x. If we do last, we get 12x. Just 12. I was about to say 12x. Combine like terms, and we get what we had originally, which just goes to prove that this and this are the same thing, just written in 2 different forms. Okay? Now that I have it factored and set equal to 0, I can use the zero product property. So if 2 quantities multiplied together equal 0, then either 2x minus 3 equals 0 or x minus 4 equals 0. So 2x equals 3, x equals 3 halves, x equals 4. So our 2 zeros are 3 halves and 4. Alrighty.